Humans can learn complex procedures just by watching other people do them. Could machines do the same? In this paper, we introduce a self-supervised framework for procedural learning, which allows machines to learn procedures from a set of unlabeled videos. Procedure learning refers to the task of identifying key steps and their order from instructional videos. Our method, like recent approaches, uses self-supervised video alignment to learn frame-to-frame correspondences across videos. We then cluster frame embeddings to identify the key steps and use their timing across videos to determine their order. The novel method we introduced, RGWAT, Regularized Gromov-Wasserstein Optimal Transport. Given a pair of videos, we begin by extracting frame embeddings using a shared encoder, which converts each frame into a high-dimensional embedding. This produces two sequences of embeddings, X and Y. To maintain good embedding structure, each sequence is regularized using a contrastive loss. This loss pulls similar neighboring frames closer together and pushes apart frames that should not match, improving temporal consistency in the embedding space and avoiding degenerate results. Next, we compute the cost matrix C, which quantifies the visual differences between the embeddings of the two videos. This cost matrix is fed into the FGWOT, Fused Gromov-Wasserstein Optimal Transport Module. FGWOT jointly considers feature similarity and temporal structure to compute an optimal alignment between the two videos. The output of FGWOT is an optimal transport matrix T star, which acts as a soft alignment between every frame of X and every frame of Y. This matrix serves as pseudo-labels, indicating which frames correspond across the two videos. These pseudo-labels serve as supervision signals for training the shared encoder. We optimize the encoder parameters by minimizing a cross-entropy loss between the normalized similarity matrix P, computed from the frame embeddings, and the pseudo-labels T star, generated by FGWAT. In the end, the model learns to align complex unsegmented procedural videos without annotations, producing clear alignment structures as visualized by the diagonal-like transport matrix on the right. Although FGWAT aligns videos by minimizing visual differences and enforcing temporal and structural consistency, it does not explicitly promote diversity in frame embeddings. Consequently, the optimization can collapse to degenerate solutions where frame representations cluster into a small region of the embedding space, leading the model to assign an entire video to a single key step, despite the presence of multiple ground truth steps. We observe this issue most prominently on the ProCell dataset, which contains complex and fine-grained procedural variations, while it appears less frequently on datasets with simpler temporal structure. To mitigate this collapse, we introduce contrastive regularization based on CIDM, applied independently to the frame embeddings of each video. This regularization encourages temporally neighboring frames to remain close in the embedding space, while penalizing temporally distant frames that collapse within a small margin. By enforcing both local smoothness and global separation, the proposed regularization prevents degenerate embedding collapse and enables the model to learn diverse and semantically meaningful key step assignments. Our method outperforms prior procedure learning approaches across every key metric: precision, recall, F1 score, and IOU. The following pictures show qualitative results of our method compared with previous state-of-the-art methods and ground truth. As it can be seen, our method RGWOT identifies key order steps and segments actions more accurately than previous state-of-the-art. Here is another example. RGWOT model aligns tasks significantly closer to the ground truth and avoids over-segmentation. This visualizes the superior procedure learning capabilities of RGWOT over previous works. By combining robust self-supervised alignment with structure-aware regularized optimal transport, our framework learns procedures directly from raw, unlabeled videos. RGWOT produces clearer alignments, cleaner steps, and more accurate temporal ordering than prior work. We believe this pushes procedural learning towards scalable, annotation-free video understanding. If you're curious, check out the full paper or feel free to reach out. We'd love to hear your thoughts.